This program is brought to you by Stanford University. Please visit us at stanford.edu.
That's it's not one definition of momentum, it's one example of momentum, and it's the one that most people are familiar with. Right? Now, you go to Lagrangian mechanics, and you remember that the Lagrangian of a particle moving in space has a term which is the mass times the velocity squared over 2. And you notice that the momentum is the derivative of the Lagrangian with respect to the velocity. That happens to equal the momentum, the same momentum. But now we have some new concept of momentum, namely the derivative of Lagrangian with respect to the time derivative of a particular coordinate. Let's call it q dot. Now, if that coordinate happens not to be the linear position of a particle, the position of a particle in Cartesian coordinates, then it may well be that this object is not mass times velocity. An example would be angular momentum, for example, where if we have a particle moving in space and it has a term in the Lagrangian which, for example, could be m over 2 times r squared times the angular velocity squared, then there's a momentum which you would get by differentiating the Lagrangian with respect to theta dot, and that's, I'm sorry, mr squared, yes, mr squared theta dot, and that would be angular momentum. It's not linear momentum. Okay, so anytime you have a system which is described by a Lagrangian, and in that Lagrangian appears time derivatives of variables, you have now a generalized notion of momentum, which is the derivative of the Lagrangian with respect to the corresponding velocity, and that's also called p. You could give it a name, you could call it p sub q, meaning to say the momentum that's gotten by differentiating the Lagrangian with respect to the velocity associated with the coordinate q, but that's a mouthful, so we just call it the q momentum, or better yet, the momentum conjugate to q, or better yet, the momentum canonically conjugate to q. It's getting long, it's getting as bad as the original thing, yeah.
That definition for canonically conjugate momentum appears to be asymmetrical with respect to time, and that there's no momentum that's canonically conjugate with respect to time, just the spatial coordinates.
Right.
So is that true?
Yes and no. There is a very useful sense in which, yeah, what you're saying is right, of course. Time in mechanics is dealt with differently than space, or at least in mechanics. In mechanics, spatial position are the degrees of freedom of the system. Time is the independent parameter that just unfolds, so to speak. And everything depends on time through a parametric dependence. Now, it wouldn't make any sense to differentiate the Lagrangian with respect to the time derivative of the time. What on earth does that mean? It doesn't mean anything. The derivative of the time the derivative of time with respect to time is just 1. So it doesn't make any sense at all. However, when you're looking at conservation laws, a simple example would be a particle. We did this last time. In fact, we talked about two particles interacting by a spring. But just to remind you, if you have a Lagrangian, for example, mx dot squared over 2, which happens to have a symmetry. This is a third definition now of momentum. First one is just m times v. Second one is partial of L with respect to q dot. Now, the third one, which is not really usually called momentum, well, it is it's not considered a definition of momentum. It's a theorem about conserved quantities. Conserved quantities include things like momentum. So momentum is a special case of a conserved quantity under certain conditions. What is the conditions under which momentum is a conserved quantity? It's the condition that the Lagrangian not change if you shift the coordinate by amount epsilon. If you shift the coordinate, x dot doesn't change. And using Noether's theorem, which we talked about last time, you can prove that mx dot is conserved. Basically, it's just a Lagrangian equation that d by dt of mx dot is equal to 0. All right. So momentum is a special case of a conserved quantity which is conserved by virtue of a symmetry. So that's another aspect of momentum. Another aspect, conserved sometimes by virtue of a symmetry. Sometimes these are the same things. Sometimes they're not. Sometimes they're the same concept, sometimes they're not. For example, there are systems where the Lagrangian involves velocities in a more complicated way. In particular, a particle moving in a magnetic field has another term that also depends on velocity, where the momentum is in fact not mv. Anybody know what the Lagrangian is for a particle moving in a magnetic field? Right. There's another term, the vector potential. The vector potential, which is a vector field, plus the vector potential dotted into the velocity with the electric charge here. All right. So for example, if I wanted to calculate the momentum canonically conjugate to x, I would want to differentiate the Lagrangian with respect to x dot. What does that give? It gives mx dot, and then from here there's another term. This here is a sub x, x dot, plus a sub y, y dot, plus a sub z, z dot, and so forth. And so there's another term which is plus the electric charge times the vector potential. So there's an example where perfectly ordinary momentum is not, well, it's not so perfectly ordinary, but where the momentum conjugate to a Cartesian coordinate is not mass times velocity. It's mass times velocity plus vector potential. So these can diverge. They don't necessarily have to be the same definition here. They may be different. Furthermore, it's quite possible that momentum for a given system is not conserved. So these really are three different concepts which sometimes converge and sometimes really define the same object. Okay. Now, what we studied, we took a field theory last time. Let's forget that it had anything to do with a string vibrating. And it was just a field theory in which the Lagrangian density, now I'll use script L means Lagrange density. The Lagrange density is equal, let me write the Lagrangian. The Lagrangian is the integral over space, dx. If there's 3 dimensions of space, this becomes d cubed x with 3 dimensions of space. And then we wrote something with a phi dot squared over 2 minus some derivatives, let's say d by dx, phi sub x squared over 2, whatever else. Now, just like we define canonical momentum conjugate to a coordinate by the derivative of the Lagrangian with respect to the velocity, we can define a thing called field momentum. Field momentum is not linear momentum. It's not a vector in space. It doesn't have a sense of direction. Ordinary momentum has a direction in space. It's a vector. So, of course, is the velocity. Field momentum is not a vector. It's a scalar, in fact. It's a scalar with respect to rotations. But its definition is just the derivative of Lagrangian with respect to phi dot. That's the canonical momentum conjugate to phi. So it's quite a different concept. has nothing to do with translation symmetry, has nothing to do with spatial translation symmetry. It has only to do with the field phi. Okay? So what is that canonical momentum? It's usually called pi, or often called pi. Pi is like p, except we're using Greek letters now instead of Latin letters. Pi is equal to the derivative of the Lagrange density with respect to phi dot. All right, so it's field momentum. Should not be confused with the kind of momentum which, when it hits you, knocks you in some direction. Okay. All right. It is invariant under a geometric rotation, right. It's not Lorentz invariant, but it is invariant under a geometric rotation of space. So this would not be the kind of momentum which, when it hit you, would knock you in some direction. There's nothing to do with motion along some axis. It has to do with motion in field space, if you like. Right? So that's another concept of momentum. Yes.
Now, last time you were going to, you did the first symmetry, which you added epsilon to phi.
Right.
And then you're going to do, you talked about another symmetry where you displace essentially x. And does that also come up with a conservation law?
Yes. That's what we're going to talk about now.
Good.
In a moment. Let me just review, though, to get back. Yeah. All right. So let me just remind you of Noether's theorem, or the slightly simplified version of Noether's theorem that we've used. If you have a symmetry, and a symmetry means an operation where you replace each one of the q's by q plus epsilon times f sub I of all of the q's. In other words, it's just a transformation with a small parameter in it. If the Lagrangian doesn't change, if the Lagrangian does not change, or the Lagrange density, let's just say the Lagrangian, if the total Lagrangian doesn't change, then there is a conserved quantity, and the conserved quantity is the sum over all the coordinates of the momentum conjugate to the ith coordinate times f sub I of q. In other words, times this small shift. You can neglect the epsilon there, just f sub I of q. And that's the conserved quantity which is conserved as a consequence of the symmetry. Now, in some cases, as I said, let's forget this over here. In some cases, it may correspond to one of the other definitions of momentum. It may be that the conserved, sometimes this is called a conserved charge for reasons that will become clear. But let's just call it the conserved quantity. The conserved quantity may be momentum. If this is Lagrangian, then let's just go through it. The delta x is just equal to epsilon. That means f is equal to 1. And the conserved quantity is just p. Just p, momentum. So sometimes it can be that the conserved quantity really is momentum. Other times it may not be. All right. So let's go back now. This Lagrangian, as it stands, has a symmetry. And the symmetry is phi goes to phi plus epsilon. Notice that this epsilon is just a number. Epsilon, it does not depend on where we're talking about. It's not that phi of x is going to phi of x plus epsilon of x. It's just phi of x going to phi plus a constant. Okay? A small constant in this case. Then we would say that f is equal to 1. And let's write out this Noether conserved quantity. It's then, in this case, it becomes integral dx. The integral dx replaces some on I. P sub I is replaced by pi of x. P sub I, well, first of all, sum on I is integral dx. P sub I becomes pi of x, with pi of x being written up here. And f, in this particular case, is just equal to 1. So this becomes our conserved quantity, the integral, which is equal to the integral dx of partial of phi with respect to t. That's as long as there's nothing in the problem which destroys the symmetry of field translation. Now, I'll tell you some things that can destroy the symmetry, which would undo this. Not undo it, but I mean, yeah, undo it or reverse the conclusion. If there was another term in here which was minus mu phi squared, for example, we talked about such terms, then this term is not invariant when you shift phi. Phi squared is most certainly not invariant if you let phi change a little bit. And so that kind of term would destroy the symmetry, and it really would. Another example is if we were talking about a string or something like a string, and the string were pinned down at the endpoints. Let's suppose we're talking about translation of the string along the vertical axis. Every point gets moved up. Well, that would be a symmetry, all right, except for the fact that by definition, the endpoints are supposed to be pinned down. If the endpoints are supposed to be pinned down, it's simply not a possible operation in the system to move all the points vertically upward. And so the symmetry, again, is destroyed. It's for this reason that you can have, let's look at a particular motion. You can have standing waves, let's say, standing waves which, go up, oscillate up and down. At this point over here, all along the string, phi dot is positive. It goes up to the top of its orbit up here, and the string comes to rest. So all the phi dots become equal to 0. Evidently, the integral of phi dot is not conserved. Okay. On the other hand, let me imagine a string. Let me give you a string connecting 2 points, which does have a conservation law. I think we talked about this last time. Instead of pinning the string down here, let's imagine a pair of poles. Not poles in any mathematical sense, but vertical poles. And let's imagine that the rope or the string was attached to these poles by frictionless rings, which are also free to slide up and down. Then, if the string is free to slide up and down, then it does mean something to think about moving the string vertically. Obviously, the action or the Lagrangian doesn't change if you move the whole string vertically upward. The derivatives, that's pretty clear. And so in that case, the integral of phi dot would be conserved. So if you started the entire string moving upward, it would just continue to go upward and upward and upward. Wouldn't have standing waves like that. It would just levitate. Okay, now let's come to some other, I want to discuss, well, 3 other conservation laws. The first we've already discussed again, and it's just energy, conservation of energy. This I'm not going to derive again. It is a conservation law which follows from a symmetry, but it's a more subtle symmetry. Go back to classical mechanics. Energy is conserved by virtue of the symmetry where time goes to time plus epsilon. Now, we're not going to get into that tonight. We're going to go back to our notes in classical mechanics and remember how that worked. It's a fairly involved little derivation. But the point is that as long as the Lagrangian doesn't change when you shift time, energy is conserved. It's almost always the case. That the Lagrangian is time independent. It's time independent in the sense that there's no explicit dependence on time. And in that case, energy is conserved. I'll remind you of the formula for energy, the general formula for energy. If the Lagrangian, I'll give you both a special case and the general case, if the Lagrangian of a system happens to be of the form that it contains velocities squared, q sub I dot q sub j dot, now this is not really squared, just quadratic in velocities. If it's quadratic in velocities, you can take the simple case where it's the sum of velocities squared. It can contain coefficients, masses, or whatever you like. Let's just simplify it and say it's some sum of coefficients. I'll call them m sub I over 2 times q sub I dot squared. This does not have to be linear motion, just as long as the Lagrangian contains quadratic things like this. All right. And also things which don't depend on a velocity. We usually call them the potential energy. In other words, if it can be written as a kinetic energy minus a potential energy, then it follows that the sum of the potential energy and kinetic energy is conserved. T plus V, T plus U. T plus U is conserved. And as I said, that is an example of Noether's theorem, but a more involved one that I don't want to go through again. We traced it through in mechanics class.
I have a question about explicit dependence of time. Does that somehow imply an external force or something?
Yeah, it usually implies some external force which is varying with respect to time. That's right. That's the sort of thing that it involves. Right. For example, here's an example. Supposing you have a harmonic oscillator. Now, if the harmonic oscillator potential is fixed, in other words, if the spring constant is fixed with time, independent of time, then the energy is conserved. The Lagrangian is then x dot squared m over 2 minus k over 2 x squared, usual harmonic oscillator. But now let's change things a little bit. Let's see, how can we imagine the spring constant changing? Can you imagine the spring constant changing with time? Yeah, the spring constant might depend on the temperature. The temperature might vary with time. We don't want to take into account all the motion in the molecules and everything else, so we're going to summarize all of this by just saying the spring constant depends on time. Now the Lagrangian has explicit time dependence. If it has explicit time dependence like that, then energy is not conserved. Of course, what's happening is energy is going from one form to another, but the mechanical energy described just by this thing by itself is not conserved. So if there's any explicit time dependence, in other words, if the parameters of the problem, spring constants, masses, other parameters, if they depend on time explicitly, then the energy is not conserved. Of course, as I said, that usually means that we've ignored part of the system and just treated it by ignoring its dynamics and just saying there was some time dependence in the system. Okay.
So in connection with that, is it the same thing to say that the partial derivative of the Lagrangian with respect to time?
The partial derivative. The partial derivative holding everything else fixed, meaning the fields and their time derivatives, yes.
Right. So
yes, that's what it means.
You've got Q's, Q dots, and T.
And
if the partial derivative with respect to T.
Absolutely. That's what it means.
That's what it means.
That's what it means. Yeah. Right. Okay.
Which goes to what's his name had said that. He said it the way you did, but he never said.
Who's he?
Gold, what's his name? The mechanical book.
Oh, Goldstein. Yeah. Well, if Goldstein was teaching this class, he probably would have said it on the blackboard when you asked the question. Yeah. Right. What the hell does that mean? Yeah. Good. All right. So let's write down then the expression for the energy for the simple field theory. Let's not include this m phi squared term. Let's just take the simple field theory. It could have more dimensions. I've written it as if space was just one-dimensional. You can add in y and z if you like. I'm not going to do it. It's too much writing. Yeah. What is the energy? The energy, total energy, is then 1/2 m x dot, phi dot squared. You have to integrate it over space. Phi dot squared. Kinetic energy plus potential energy, and that means plus, in this case, phi, so let's see, not m, just phi dot squared, plus phi sub x squared, and if you like, plus phi y squared, blah, blah, blah. In other words, it's the sum of the square of the time derivative and the space derivatives. That's the total energy. Notice that it's always positive or 0. Let's in fact look at it. Let's compute it. Let's take the case of waves going in one dimension. So our field now has some profile, and let's imagine a wave moving in the positive x-axis. That means it has some profile, but its full dependence is not just phi of x, but phi of x and t, and it has the form phi of x minus ct. Oh, are there some c's in here? Yeah. As it stands, it's not dimensionally consistent. This is a derivative with respect to time. This is a derivative with respect to space. So I think we have to put a c squared here. C is space over time. Yeah, that's right. We have to put a c squared here. Okay. Now, if we solve the equations of motion, we find out that there are solutions which just move rigidly down the x-axis or up the x-axis, two kinds of solutions. Let's take the right-moving solution. There's also a left-moving solution where we would change the sign of the change the sign of the CT term. And let's calculate this. Phi dot squared plus c squared d phi by dx squared. Okay, this is phi. Phi does not depend on x and t separately. It depends on the combination x minus ct. So what is phi dot? D phi by dt. That's the derivative of f with respect to its argument. Shall we just call f f prime? F prime means the derivative of f with respect to what's inside its argument here, times the derivative of the argument with respect to t. That's minus c. So that's minus c times f prime. That's the derivative of phi with respect to t. And the derivative of phi with respect to x, that's just f prime. Differentiation with respect to x just gives f prime. Okay, so what is the energy then? The energy is the integral is 1/2 the integral phi dot squared, that's c squared f prime squared. That's the first term. And then the second term is another c squared f prime squared. In other words, just forget the factor of 2 and get rid of one of these. That's the total energy of a wave moving to the right, integral dx. What about a wave moving to the left? Well, the difference for a wave moving to the left, here's a wave moving to the left. I would change the sign here, but it would not change the sign of the square of d phi by dt squared. So once again, it would be exactly the same expression, 1/2, let me remind you what it was, 1/2 the sum of two terms, one of which was c squared f prime squared over 2, and the other of which was c squared f prime squared over 2. All right, same thing. The square of phi is not going to change. The square of phi dot is not going to change, so this term won't change. It'll be exactly the same. And so the energy of a left-moving wave and a right-moving wave are the same. That's not surprising, of course. And in fact, it wouldn't change if I rotated the wave into some other direction if I were doing it in 3 dimensions. The profile of the wave counts, but not which direction it's moving in. So let's just write this out. That's the energy. Good. Any questions about energy conservation? Yes.
You use the constant c suggesting the speed of light.
Oh yeah, that's the speed of light. Sorry.
So
Yeah.
if your field theory,
Or the speed of propagation.
so if the speed of propagation is not equal to the speed of light, then it's still Lorentzian transform.
No, it's no. You see, no. Okay, let's talk about that. Supposing this was sound, all right? You would put in there the speed of sound. Okay, would that make sound Lorentz invariant? Well, it would be true that the sound wave theory would be invariant under certain transformations, but they would be the Lorentz transformations with the wrong speed of light. Okay? Okay, so you say, so what? It's invariant with respect to the Lorentz transformations with the wrong speed of light. But then there would be other things. For example, the mechanical motion of particles or other waves, which might be described by a Lorentz invariant theory with the right speed of light. The combined things together would not be Lorentz invariant in the usual sense. So.
Fields, like the Higgs field and
Oh, they all have the same speed of light.
all have the same speed of light.
Right. Miracle. And one has a perfect right to ask, why is that so? But it's, well, you even have a right to ask, how do I know that? Okay. We know it, well, the way we know it is because these things tend to influence each other. The Higgs field affects the electron motion, affects the photon in various ways, and they all get mixed up together in a rather serious way. If there was any violation of Lorentz invariance, it would infect its way through the rest of the physics, and we would know about it unless it was extremely minute, unless the violation of Lorentz invariance was extremely minute. So, for example, just take electrons and photons. The maximum speed of an electron is believed to be exactly the same as the speed of light, believed to be exactly the same. Therefore, they both sets of objects, photons and electrons, are invariant under the same Lorentz transformation. Okay. What if the maximum speed of electrons were slightly different than the maximum speed of photons? Or if the speed of gravitons were a little bit different than the speed of photons? Okay. Then the physics would not have an exact Lorentz invariance because the two pieces of the physics would have different Lorentz invariances, and the combined system together wouldn't have a single Lorentz invariance. As long as electrons interact with photons, those are going to get themselves mixed up in a way that they're going to affect each other. And we would know about it from very, very high precision quantum electrodynamics experiments and so forth, unless that velocity difference was sufficiently small that numerically we couldn't distinguish. Yeah.
If you were moving the opposite direction of the sound wave relative to you would still asymptote at c, right? So in that sense, it's...
No. If you were moving relative to a sound wave, you will see that sound wave move with a different velocity than the speed of light, than the speed of sound.
Right, that's what I mean.
Yeah.
And it will increase, but
Yeah.
asymptote to c.
Asymptote with respect to what? When you say something asymptotes, you have to say asymptotes with respect to something.
To c.
No. Asymptotes with respect to some process. I mean, with respect to some...
Well, the addition of velocities...
sorry, wait. There are two C's in this problem now. There's the speed of sound and there's the speed of light. Let's call the speed of sound...
Yes, so I'm saying the speed asymptotes to the speed of light.
Okay. So, yeah, you're saying supposing a sound... Good. You're saying supposing a sound wave was going down the x-axis, and relative to you, it's moving with what, 1,000, is it 1,000 feet a second or something? Something like that. moving 1,000 feet a second, but there I am zipping down the axis with very, very close to the speed of light. Then I would see the sound wave moving very close to the speed of light.
That's right.
Yeah.
And in that sense, it's Lorentz invariant.
And that's, well, in that sense, but I don't think that's worth too much, frankly. Yeah. Okay, so that's the energy, c squared times f prime squared. Next, I want to come to the concept of linear momentum for fields. Now, this is not a momentum which is conjugate to the field. This is actually the stuff which, if it hit a particle, it would make the particle move off along some axis. In particular, it's a momentum which will be different for waves going to the left from the right. In fact, for waves going to the right, the momentum will point that way, the linear momentum will point that way, and for waves going to the left, the linear momentum points the other direction. So this is part of the ordinary momentum, but it's part of the ordinary momentum which is carried by waves. In quantum mechanics, it becomes the ordinary momentum carried by photons, for example. All right, so it's the ordinary momentum as carried by the waves. What does it have to do with? Well, ordinary momentum has to do with translation invariance. So we can ask, is this Lagrangian here invariant under translation, spatial translation? And if so, what is the conserved quantity? And this is a little bit subtle. It's a little bit abstract, but I'm going to run you through it, and I'm going to work out for you what the conserved quantity that we identify with translation invariance is. Okay, let's imagine that we take a wave. Let's say that it's phi of x. We don't need to worry about its time dependence right now. It's got some profile phi of x, and we take the whole wave and we move it a little bit. We rigidly move it. If you take a look at that Lagrangian, it's quite obvious that the integrated Lagrangian won't change. All I've done is I've displaced everything uniformly, and that should not change the total amount of kinetic energy or the total amount of potential energy. It may change the kinetic energy at each point, but all you're doing is substituting this point over here for this point over here. After the wave has been displaced a little bit, if I do displace it, or if I imagine displacing it, then anything that was originally going on over here, exactly the same thing is now going on over here. Anything that was going on over here is now going on over here. So when I add up all the terms in the kinetic and potential energy, then after I shift the wave a little bit, they will be the same, kinetic and potential energy. Not the kinetic energy the same as the potential, but the kinetic energy before and after. All right, so how then does phi of x change when I displace the field a little bit? It does change if I stand at a particular point. If I'm the eye in the sky over here looking at that point, and I shift the wave, this is not an upside down A, it's an eyeball. And I'm staring right at the field where I am, and I shift the wave a little bit, the field changes. So this shift of the field is associated with a small change in phi. How much does phi change if I shift the field to the right a little bit? What's the change in phi? Let's write the change in phi if I shift the field to the right a little bit. Derivative of phi with respect to x times delta x. Now, is it plus or minus that? This is the hardest thing in the world to figure out. Okay, let's check. Supposing phi, you think it's minus?
I think that the dot curve is...
I also think it's minus, but I'm not sure why.
You're moving backwards.
Yeah. I think it's minus d phi dx times delta x, right? It's either one or the other. It's the rate at which phi is changing times the amount that you shift by. Okay, so that's the change in phi. At every point in space, phi changes by amount this much. Well, that's an example. It's a special case of this idea that delta q, the change in a q, is epsilon times a function of all the q's. In this case, epsilon is just epsilon, but f of q is the partial of phi with respect to x. That's what represents f of q, the small displacement or the small change in phi when I do the operation. Now we can very easily calculate the conserved quantity. Remember what the rule is for the conserved quantity? I erased it off the blackboard, but it's just to take pi, multiply it by f, and integrate over space. That's the same as sum of p sub I times f sub I of q. So we take f of q, we multiply it by the canonical momentum, and we integrate it over all space, and that gives us a quantity. Let's just call that quantity, I don't know what to call it. Let me call it p. P because, in fact, it really is a certain momentum. All right, what is it? It's given by d phi by dx, I guess it's minus d phi by dx, times pi sub x integrated over all space. That's the momentum which is conserved by virtue of the invariance of the Lagrangian with respect to spatial translation. That's a mouthful. The quantity which is conserved by virtue of translation invariance. Okay. What is pi x? Where do we have it? Pi x is just phi dot. So for our special case, this is just minus the integral of d phi by dx times d phi by dt. That quantity is conserved, as I said, by virtue of translation invariance. Let's suppose that our system that we were talking about was a combination of particles and waves, electromagnetic radiation and electrically charged particles. Supposing I displace all of the waves, all the electromagnetic waves, by distance epsilon, but I don't displace the charged particles. Do you expect the dynamics to be invariant under that translation? No. No. In fact, if I displace the radiation so that it moves away from the charged particles, that obviously changes things, changes energies and so forth. But supposing I displace the waves and the charged particles together, then I do expect that the Lagrangian not change. So in such a situation, I would expect that the total momentum would have a contribution coming from it from terms having to do with the electrons and terms having to do with the waves. What would be the part of the momentum that would just correspond to the electrons themselves? MV for each electron. What would be conserved? The thing that would be conserved would be the field momentum plus the ordinary momentum of the charged particles. So this thing actually deserves to be called the ordinary momentum associated with the field itself. In fact, roughly what we prove by this line of argument is that if this field were to interact with a collection of ordinary particles and bump them, push them, and do whatever it does to them, that the momentum of the particles plus the field would be conserved if the Lagrangian is invariant under a total shift of everything simultaneously. That's why this is called it's not called the ordinary momentum, it's called the momentum. But which momentum? Let's call it the ordinary linear momentum. Okay? Let's calculate it for our right-moving wave. Now, it's quite possible that I've got the sign wrong here. We will find out if I got the sign wrong, because any fool can see, including me, that a wave that's moving to the right should have a positive momentum, and a wave moving to the left should have a negative momentum. So if I've got the sign wrong, we'll find out. We'll find out because our right-moving wave moving down the positive x-axis will wind up having negative momentum along the x-axis. That's a bad thing. So we'll change the sign, but let's do it. Okay, let's, here we are again. d phi by dt is c times f prime. We want, this is the left mover. I want the right mover, and then there's a minus sign here, right? Yeah. Now we have a right mover, and what do we have then? We have d phi by dx times d phi by dt, and that looks to me like the linear momentum is the integral dx of minus, looks like I got it right, minus d phi by dt times d phi by dx. That gives me a factor of c, another minus sign, and f prime squared. Fortunately, I seem to have gotten the sign right, and the linear momentum of the right moving wave is positive. Notice that it's closely related to the energy of the right moving wave. In fact, apart from a factor of c, the energy and the momentum are equal to each other. In fact, we can write that this is equal to c times p. There's an extra factor of c in the energy that's not there in the momentum. What about a wave moving to the left? That's like this. That changes the sign of this one, makes it plus, and changes the sign of the momentum, since the momentum has a natural minus sign in it. P in that case becomes minus this. So a wave moving to the left, the momentum is exactly the same, except that it's moving in the opposite direction. Well, it's exactly the same, except that it's exactly opposite in sign. It's not hard to work out the more general case where a wave may be moving in an arbitrary direction. And of course, the answer is that momentum is a vector. This kind of momentum is a vector, and it points along the direction of motion of the wave. But these are two simple situations. So we can then write, for these kind of waves, that energy and momentum are related. Let's write down the general relationship. Momentum is a vector. P is a vector. And the energy, a spatial vector, an ordinary 3 vector. Energy is a spatial scalar. And energy is equal to c times the magnitude of the momentum. You know any particles that have this property, that their energy is equal to c times their momentum? Photons. 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 In fact, any particle that moves with the speed of light has the property that its energy is equal to its momentum times c, or the absolute value, the magnitude of its momentum times c. So we've discovered another conservation law, the conservation of linear momentum, and the formula for it doesn't involve phi dot squared and phi x squared, but involves the product of phi x and phi, d phi by dx and d phi by dt. Okay. Yeah.
If I was in 2 dimensions and I had a wave that was symmetrical about the origin, does it have 0 momentum?
Yeah. Yep.
Even though it's carrying energy?
Yep. You're thinking about a spherical wave or a circular wave. Yeah. Somebody makes a puddle, you know, a wave going out in ripples. 0 total momentum, but it does not have 0 momentum density. I have not talked about the concept of energy density and momentum density. We will. We need to talk about that. This is a good example, good reason. But yes, it has overall total zero momentum, even though it has zero energy, even though it has non-zero energy. Okay, let's take a 5-minute break, and I'm going to take a 5-minute break. I'll be back in a few minutes. Okay, let's talk about another conserved quantity. Now, this conserved quantity is associated with a particular kind of field, a field whose field variable is complex. Now, a complex field, complex in the sense of complex numbers. The complex number z is just a real part plus I times an imaginary part. Or we could call it z1 plus I z2. So every complex number is just a pair of real numbers, but you deal with it in a certain way by certain rules. The complex conjugate of z is equal to z1 minus I z2, or x minus iy. Let me just write down some simple facts about complex numbers to just remind you. Star. Complex conjugate. What else do we need to know? Z star z is just x squared plus y squared, or z1 squared plus z2 squared. And finally, every complex number can also be written as a magnitude r times e to the I theta, where theta is an angle between 0 and 2 pi. It represents the position of the complex number x, y, or it can also be written in terms of r and theta, r e to the I theta. Oh, last thing, z star is r e to the minus I theta. All right, that's your course in complex numbers. Now, a complex field, on one level, can be just thought of as a pair of real fields. Just for some reason, there are two fields in our problem. They're very similar to each other. They have very similar properties, and we just call them phi 1 and phi 2. Or we group them together, and possibly just for some notational convenience, we write that phi is equal to phi 1 plus I phi 2. We also write that phi star is equal to phi 1 minus I phi 2. The derivative of phi with respect to any coordinate is equal to the derivative of phi 1 with respect to x mu plus I times the derivative of phi 2 with respect to x mu. Incidentally, 1 and 2 here do not mean derivatives. They just mean real and I think I might have done better to call it phi real plus I phi imaginary, but I've already committed myself. Phi 1 plus I phi 2. So I'm not using the subscript notation now to indicate derivatives. All right, so the real and imaginary part of derivatives are just the derivatives of the real and imaginary part, and so forth. It's all very simple. Now let's write a Lagrangian for this pair of fields. The two fields are very similar to each other. Each one has the same kind of Lagrangian that we've written before, namely L equals integral d3x. Or I might have just written the Lagrange density, but let's write it down. Phi 1 dot, meaning time derivative squared, over 2, plus derivatives with respect to spatial position of phi squared over 2, sub 1. X, y, z, all of them can go in here. And I might even, for fun, add in plus mu over 2 phi 1 squared. I might also add in many other things, but, oh, sorry, minus. I think we got some minus signs here, huh? Minus signs. All right, everybody recognize that for phi 1? just the same kind of Lagrangian we've written down in the past. I've added in this mu term, the so-called mass term. All right, that's for 1. Now what about for field number 2? That also enters into the Lagrangian. Same thing, phi 2 dot squared over 2 minus dx phi 2 squared over 2. Add in y and z derivatives if you like, but let's also add in minus mu over 2. Same mu, phi 2 squared. I can use the complex notation to simplify this. First of all, let's concentrate on this phi 1 squared and phi 2 squared. Phi 1 squared plus phi 2 squared is the same as phi star phi. That's just phi star phi. What about phi 1 dot squared plus phi 2 dot squared? That's phi 1 dot, that's phi dot times phi star dot. A 1 squared plus a 2 squared always means a thing times its complex conjugate. So all of this can be simplified into the form integral dx phi dot star times phi dot over 2. This stands for phi 1 dot squared plus phi 2 dot squared. Likewise, for the spatial derivatives, dx phi star times dx phi over 2. And finally, minus mu over 2 phi star phi. This Lagrangian, of course, has all of the symmetries that we've discussed so far. Well, it doesn't have the shifts, it has some of the symmetries. In particular, it has energy conservation, it has momentum conservation, but it has a new symmetry and a new conserved quantity, one that plays a very major role in particle physics and quantum mechanics, but we're studying it at the level of classical physics at the moment. Anybody know what that symmetry is? Yeah, right, exactly. Let's take phi and multiply it by e to the I epsilon. Epsilon is any complex, any real number now. Any real number. What does that do in terms of the, if we plot phi on the Cartesian axes in terms of a real and imaginary part? It just takes phi and rotates it a little bit. It rotates the angle, theta a little bit. So it rotates phi in this direction, it rotates phi star in the other direction. This is a particular operation that we can do on phi. Okay. Epsilon, I'm imagining for the moment that epsilon is very small. Let's imagine epsilon is very small. We don't have to, but I want to make contact with the idea of a small transformation involving a small parameter epsilon. If epsilon is small, what is e to the I epsilon? It's 1 plus I epsilon. 1 plus I epsilon if epsilon is small, plus things higher order in epsilon. That's just a formula that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, blah, 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 blah. If I terminate this after the first term for very small values of x, then e to the x is 1 plus x. E to the I epsilon is 1 plus I epsilon. So for small epsilon, what we're doing is multiplying phi by 1 plus I epsilon. Now, is that a symmetry? Is the Lagrangian changed if I multiply phi by e to the I epsilon? And here it's obvious that it doesn't change. Phi star phi does not get changed when I multiply phi by e to the I epsilon. The e to the I epsilons cancel when you multiply phi times phi star. And so phi times phi star or anything, phi times phi star, phi dot times phi star dot, you know what I meant, phi star dot times phi dot. Any of these expressions involving a star times an unstarred thing will not change if you just multiply phi by e to the I epsilon.
That's because it changes phi star.
Say it again?
Phi star e to the I minus I.
Yeah, exactly. When phi, if you multiply phi by e to the I epsilon, then you must multiply phi star by e to the minus I epsilon. So if you change phi by an amount e to the plus I epsilon, you change phi star by a factor e to the minus I epsilon. In other words, you can write that the change in phi under this kind of transformation is I epsilon times phi. Right. What is the change in phi star? It's minus I epsilon times phi star. Does everybody see where I got this from? I just said the change in phi is I epsilon times phi. That's the little change here. And if I do the same thing for phi star, I find out that it changes with a negative thing over here. Okay. Is this a symmetry? Yes, it is a symmetry. The Lagrangian does not change because it always involves things like phi times phi star. Is there a conserved quantity associated with it? Yes, there is. I'll show you the little manipulation. You can go home and work it out without using complex notation. I'm going to use complex notation. I'm going to do a slight cheat on you. But you can go home and check what I've done by using the actual real components of phi in the Lagrangian. But here's the trick. There are two independent components of phi. I'm going to pretend that the two independent components of phi are phi and phi star. You can check that this will actually work and give you the right answer. So here's the idea. What is the canonical momentum conjugate to phi? The canonical momentum, here it is. Here's our Lagrangian. What's the canonical momentum conjugate to phi? It's the derivative of the Lagrangian with respect to phi dot, right? That's its definition. But that's just phi star dot. So this is phi star dot. What's the canonical momentum conjugate to phi star? That's the derivative of the Lagrangian with respect to phi star dot. That's phi dot. Pi conjugate to phi star is equal to phi dot. No, yeah, I guess there is an over 2. Yeah, you're right, there is an over 2. I missed that. Yep, there is an over 2. It won't affect the value of the conserved quantity. Now, these two expressions are shorthands for the momentum conjugate to phi 1 is phi 1 dot, and the momentum conjugate to phi 2 is phi 2 dot. They're shorthands for that, and they really just represent that. Notice that the canonical momentum conjugate to phi star is the complex conjugate of the canonical momentum conjugate to phi. They're complex conjugates of each other, pi and pi star. Okay, now let's work out the conserved quantity. The conserved quantity, we know what the change in phi is. Remember what in other words, we can say f sub phi is I times phi, and f sub phi star is minus I times phi star. Remember what f is? Everybody remember what f is? It's the small change in phi except for the factor epsilon. Same f as in Noether's theorem. Now it's straightforward to work out. I'm going to work this out for you another way. I'm using a fancy notation, the complex notation for something which we'll do another way. Let's do it this way. What's the conserved quantity? It's pi sub phi times f sub phi, pi sub phi, f sub phi, plus pi sub phi star times f sub phi star. Now what have I left out? Integral over space. That's the summation over I. The analog of the summation over I is the integral over space. Let's see what it is. Pi sub phi is phi star dot over 2. So this is here equal to, did I leave an I out somewhere? No, I didn't. Phi star dot over 2 times f phi, and f phi is I times phi. That's one term. Now the second term, pi sub phi star, that's phi dot over 2. And now f sub phi star, but that's minus I times phi star. So there's a minus I times phi star. That's the most untransparent and least obvious expression I think I've ever written down on this blackboard for you. Phi star dot times phi minus phi dot times phi star. Integrated over space. Let me just derive it another way which doesn't make use of this fancy complex notation. Let's write phi is equal to phi 1 plus I phi 2. And now, again, I'm going to multiply. Let's see what happens to phi 1 and phi 2 under this transformation. Let's just do it. Phi 1 plus I phi 2 gets multiplied times e to the I epsilon, which is 1 plus I epsilon. And this is equal to phi 1 plus, or minus, excuse me, minus phi 1 plus I phi 2 plus I epsilon times phi 1 plus I phi 2. All I've done is multiply it out. What's the change in phi 1? Well, phi 1 is by definition the real part of this expression. The change in the real part, let's look at it. There's a real part from here. The real part of I epsilon times this thing here is minus epsilon times phi 2. I times I is minus 1, epsilon times phi 2, and then there is plus I epsilon phi 1. Phi 1. Here's the rule. The change in phi 1 is equal to minus epsilon phi 2, and the change in phi 2 is equal to epsilon times phi 1. Now you just go through Noether's theorem using this form for the changes of phi 1 and phi 2, and you'll find exactly the same expression for the conserved quantity, written in terms of the real and imaginary part. I'll leave you to do that. Substitute in the real and imaginary parts and just work out what the right answer is. But this formula is quite neat. Phi 1 star times phi minus phi 1 star dot times phi minus phi dot times phi. I'm losing it. It's getting late. Phi star dot phi minus phi dot phi star. Okay. Anybody know what this conserved quantity corresponds to in physics? No? Well, it is a kind of angular momentum, but it's not angular momentum. It, first of all, doesn't have an axis associated with it. What axis would you be talking about? No axis. It contains only it contains only time derivatives, so it has no vectorial sense to it. Angular momentum is a vector, so it can't be that. Yeah. Electric charge. Electric charge of what? Electric charge of the field. That's right. Now, where are we going? We're going slowly creeping up on ideas of quantum field theory. Remember that when we finally get to think about the relationship between particles and fields, that every field has associated with it field quanta. Every kind of particle is a quantum of some field. So photons are quanta of the electromagnetic field. Now, they are not, in any useful sense, complex fields. The electromagnetic field is real. The electron is also the quantum of a field. It's not a field that you're used to thinking about. It's not a field that you measure easily in the laboratory with a field detector. But electrons have fields associated with them. They are the quanta of the field. They're not fields which exert forces on electrons. They are the fields whose quanta themselves are the electrons. They're fields which are made up of flowing electrons, if you like. Other particles in nature, quarks. Quarks are also charged particles, and they also are described by fields, meaning to say that, that they are the quanta of fields. Charged particles are always described by complex fields. Complex fields, this is the expression for the electric charge carried by such a field. It's an integrated thing, which means that the thing in the brackets here is a kind of charge density. If this is the thing that you integrate over space to find the total charge, then the thing in the bracket here must in fact be the density of charge. You integrate a charge density over space to find the total charge. This must be it. So this expression in here actually stands for charge density. And if you think of the field and its relationship to a collection of a large number of particles, then this is just the field description of the average charge density of the particles that make up the field. Now, this really hits home only really when we get to quantum field theory, where the relationship between particles and fields becomes more manifest. But for the moment, you can simply imagine that a field moving along has an electric charge. What happens if this field interacts with the electromagnetic field? Well, the electromagnetic field may collide with this field and scatter it, much as if this were a collection of charged particles being influenced by the electromagnetic field. The motion of wave packets of this field might follow trajectories which are similar to the charged particle trajectories in an electromagnetic field. So we're not getting deeply into quantum field theory at this point, but this is a conserved quantity, which is, when we move on to quantum mechanics and to quantum field theory, does become the electric charge of the quanta described by the field phi.
You want to give a name to the integrand?
Charge density. Charge density, right. Now somebody, yeah.
Do they describe electromagnetic fields?
No, they don't describe electromagnetic fields. They describe the electric charges which are sources of those fields and which are acted on by those fields. They're not electromagnetic fields. They're not electric and magnetic fields, this phi. They are the fields whose quanta are electrons.
This is sort of classical, right?
Yeah, this is classical.
Except for the fact that you have the complex fields. So
no, that's classical. That doesn't make it non-classical. Right.
Okay. Well, then, if you is there an example where you can plug that in and show how that comes out charged? Like
Yes. Yes. But in order to see that, we would have to couple it to the electromagnetic field. And I'll tell you how to do that eventually. All right. So this is Lagrangian by itself, which is not yet coupled to the electromagnetic field. So it's a system of charged particles, but with no electromagnetic field around. All right. We will have to change this Lagrangian a little bit when it comes in contact with the electromagnetic field. And then the sort of thing we would like to see, for example, is that a wave packet of this, if we had a wave packet which looked like this, moving down the axis in this direction, and it encountered an electric field in this direction, we would like to see that what it does is to bend the trajectory of the wave packet in the same way that an electromagnetic field would. So obviously we have to do more work to see that. At the moment, this is just a conserved quantity. This is a conserved quantity, but why did I do it? I did it because ultimately it becomes electric charge. And not just electric charge. Many, many different quantities in physics, electric charge, isotopic spin, all the various different conserved quantities that are associated with particles, color charge, strangeness, all of those various quantities are described by complex fields like this, or things very similar to this.
Can you do the same or similar thing with two real fields and a rotation?
Yeah, that's what this is. That's exactly what oh, sorry, where did I write it? When I wrote it in terms of phi 1 and phi 2, which I seem to have erased somewheres, that was exactly the rotation properties of two real fields.
You can get the same point.
Oh, absolutely, yeah, it is the same. Yeah, now let me give you another perspective on it, which might be helpful. I don't know, might not be helpful. But let's come back to the string. So we have the string connected between 2 points. But now I want you to imagine that the string is vibrating not just in the vertical direction, but also the horizontal direction. So that if we projected it onto a plane, at any point the string would be the string would intersect the plane at a point. Okay? Now, that means that the actual configuration of the string is described by two fields, one of which can be thought of as the y component, and the other could be thought of as the z component, or we could just call them phi 1 and phi 2. The two components of the position anywheres along here, the string intersects, here's the origin, the string intersects the plane at some point, and it can be described by a complex field. Phi, which could be phi 1 plus I phi 2, or phi 1 plus I phi 2. So if we had a string which was free to move in two directions, x and y, we could describe it either by two real fields, one describing the x position of the field along the string, the other describing the y position. Or we could describe it by a single complex field, a point on the complex plane. What would you guess that for the mechanical analogy, what would you guess that this corresponds to? Anybody got an idea? Somebody actually said the word before, however, in a different context. It's the angular momentum of the string, but the angular momentum of the string the angular momentum of the string about this axis. In other words, this string, if you focused on a point on the string, it would be moving. It would be moving back and forth in various ways. At any given instant, it might have an angular momentum about this axis. This is nothing but the angular momentum of that string about the longitudinal axis. So here's an example.
When you say this, you mean the whole integral?
Yeah, the whole integral. Yeah. The whole integral sums up the angular momentum of each point along the string. Right. So, and the angular momentum density would be this. Now, this is not this is in the analogy of field is like string, is like violin string, electric charge is like angular momentum in the plane in which the string is moving. Okay? So, for example, a possible motion of such a string. Possible motion could be a standing wave oscillating up and down, or a standing wave oscillating in and out. But there are also oscillating waves which just circulate around like this. You take this bent string, you give it a velocity into the blackboard, and what does it do? Jump rope, rope skipping. Rope skipping, yeah, that's the analogy. Rope skipping, when the children play rope skipping, they're giving the rope an angular momentum about the axis defined by the distance between the two children. That angular momentum is a natural analog of electric charge for this system here, for the system of a string. We're not getting yet into quantum field theory, but what do you know about angular momentum in quantum mechanics? It's quantized. Happens to be quantized in units of h bar, but especially it's quantized. It comes in discrete multiples of something. What do you know about electric charge? It comes in discrete multiples of the electric charge of the electron. Is it a coincidence? Well, maybe it's a coincidence, but it has a common description in terms of fields, a similar description. Yeah.
There's not counting quarks.
If we can't, yeah, I mean, right. Quarks count everything. Count all charged particles. But
quarks don't come in discrete multiples of the charge of the electron.
You're right. Discrete multiples of the charge of a quark.
Can you actually
You're right.
put this in a...
But that's a subtle business. That is a truly subtle business, the fractional charge of quarks. So I'll ask you to forget about it for the moment, but maybe we'll get a chance to come back to it.
Is there an example where you just have, say, instead of a string, an actual electric field that can be expressed as the complex?
Yeah.
And
you could take an electric field of a charge, not the electric field, you could take the electric field associated with an electromagnetic wave. An electromagnetic wave going down the z-axis has an x component and a y component, Ex plus IEy. You could, that is to say, you could make a complex electric field, Ex plus IEy, call that and then a circularly polarized wave would have this aspect of being like the jump rope, all right? In that case, it wouldn't be electric charge. It would be genuine angular momentum of the field, because it really corresponds to a spatial direction. It really corresponds to rotation of real space, not rotation of this fictitious space.
So what's the simplest example where you can clearly show that it's a charge that's being conserved?
No, I say you have to study the connection between this and the electromagnetic field. And then you can show it's strong.
They have to be two separate fields together.
Yeah. You have to take the electromagnetic field, which means the vector potential, and couple it in the appropriate way to this, and then show that a wave packet of this stuff will move as if it were a charged particle in the electromagnetic wave. And that's feasible. We might even get to do it, but not tonight.
There's an I in the front of that envelope.
Right here.
So
yeah. No. This is the complex conjugate of this. What happens if you take the difference of two things, a thing and its complex conjugate? Yeah. So the difference between this and this is pure imaginary, and when it multiplies this, it's pure real. Good. That's a good point. If this were plus, then we'd start to worry about it. But it's minus, which means that this quantity inside the bracket is imaginary.
Oh, in fact, you get rid of the I over 2, so
yeah.
That is just the real part.
Yeah, that's right. You know,
That's what I thought, because you were almost there with the, you had already written that pi star, or you didn't write, but you mentioned that pi phi star
yeah,
is the complex conjugate of pi phi.
yeah,
Okay, and you also have actually f phi star is the complex conjugate,
yeah,
of
yeah,
f phi.
yeah, yeah.
And so you already have integral dx pi phi
Right.
f phi plus pi phi f phi star.
Yeah.
And that's already
Right.
the real part.
Let me show you one more thing. If we were talking about the string, then the phi's themselves would become the coordinate position, x and y of the string. What would the phi dots be? Velocities. This would be the cross product of the position and the velocity, which is called the angular momentum. X times Vy minus y times Vx is exactly what this would be. So the mathematical structure of this thing is very much the analog of the mathematics of the rotation in an extra couple of dimensions. It's not totally surprising that particle physicists are always interested in extra dimensions. Yeah.
We talk about the electromagnetic field and the gravitational field, but then you come and you say the field whose quanta are electrons. Is there a common name for that field? And
Common name? Quantum field. Every particle type is associated with a field. Every field type is associated with a particle. And associated with the same connection that connects photons to the electromagnetic field. The electromagnetic field comes in discrete quanta of energy, called photons. Those photons are particles. They can be isolated one at a time. They can be sent through slits. They make clicks when they hit photodetectors, and they behave like particles when they're sparse enough. In the same way, charged particles, in the opposite way, charged particles can be grouped together to form something which is similar to a field. And those fields come in discrete packets of energy that describe particles. If it's a charged particle, it must be described by a field which is capable of describing that charge. So the field has to have a conserved quantity associated with it. And in a sort of coarse-grained, you can, roughly speaking, you think of the field as a sort of coarse-grained description of the charges. The coarse-grained description of the charge is just this quantity composed out of the field.
so there's probably 50, 100 elementary particles, so there's 50, 100 fields too.
No.
Well, and presumably
No.
you could have a proton field too, right? So
What?
Could you have a proton field so it's not an
Yeah.
elementary particle?
Right.
About non-charged particles.
Well, the proton field would be a construct that you would build out of quark fields. But yes, you would have a proton field. The molecular fields, fields for describing molecules, fields that describe bowling balls. It's just not a very useful concept for bowling balls. It's hard to build a kind of coherent, simultaneous motion of a lot of bowling balls but in principle, yes. Somebody was going to ask a question.
Yeah, you talked about the relationship of charged particles to electric fields. What about particles that don't have a charge?
Wait, say it again?
Particles that don't have a charge, neutral particles, do they relate to an electric field as well?
Do they what?
Do they connect the same way a charged particle would to the field? You were talking about charged particles.
Uncharged particles are also described by fields, but those fields don't interact with the electromagnetic field. At the moment, we haven't described the connection between these charge-carrying fields and the electric and magnetic fields. They're different animals. They have different symbols. Electric field is E, magnetic field is B. This is neither of them. This quantity that's in the bracket here, what would you call that in electrodynamics? Rho. Standing for what? For charge density. How about current? Can you guess? Can you make a guess? If this is the electric charge density, what would anybody like to venture a guess? No, that's not a bad guess. But the reason it can't be right is it's got to have a direction of space associated with it. The current flows in a direction. Current is a vector. No, rho dot doesn't have a sense of direction. Rho dot is connected with the current. It's the divergence of the current, but the...
Derivative of momentum?
It's very simple. Let me rewrite this. This is the charge density. Its derivative with respect to t of phi star times phi, and then minus another term with an I. One half of it. X, Y, Z, in other words, derivative of phi times the derivative with respect to xi, I could be x, y, or z, times phi star. That's a thing now that has a vector index. This has a direction in space. It could be derivative with respect to x, could be derivative with respect to y, could be derivative with respect to z. When you combine it with the derivative with respect to t, you get 4 components. The 4 components form a 4 vector. That 4 vector is composed out of the electric charge density and the electric charge flow, the usual electric charge current. So a very similar kind of thing, except not with time derivatives, but space derivatives, forms the electric charge current. We haven't gotten to it, but we will get to it. Any other questions? Good. We got a few minutes.
What would the, in the example of the wire, what would the conserved quantity be for current flow for J?
For a wire? Right. Well,
charge density corresponded to angular momentum.
Oh, you mean for the, sorry, for the, yeah. Oh, the wire, you mean the jump rope? Jump rope. Yeah, just exactly this. This would be the flow of charge along the x-axis, or the flow of angular momentum along the x-axis. There is a notion of angular momentum density, which can be just identified more or less as the angular momentum of each particle in the jump rope. But now if you have a wave going down the axis, imagine, okay, so we have a rope, and we start twirling it like this. Waves go down the axis, but they're sort of circularly polarized waves. In that case, there's a flux of angular momentum. Angular momentum is traveling down the string, and that traveling angular momentum is the analog of the electric charge current. Right. Of course, it's a different thing. I mean, you don't have to take a wire and spin it in order to make electric charge go down it, but you have to spin it in this internal space, this fake space of phi 1 and phi 2. Yeah. So this gives you some idea, if nothing else, about why, as I said, why particle physicists do have an interest in internal dimensions, that the quantum numbers, the conserved quantities that are associated with particles, often, in fact always, can be considered motions in hidden spaces. Now the hidden spaces may be purely mathematical, or they may even be hidden spaces, but one way or another, the mathematics of these conserved quantities is very closely related to the mathematics of motion in extra spaces, and in particular angular momentum type quantities in extra spaces, extra dimensions of space. So that's where we may ultimately get to, maybe.
What would be your symmetry transformation to get to J?
No, J is not a conserved quantity. It's the integral of rho, which is the conserved quantity. J is a flux of a conserved quantity. So, for example, let's see, and here's a sense in which J is not a conserved quantity. You can have a flow of charge down an axis here, okay? Some other kind of object, a photon coming here, scatters these particles and turns them around and turns their direction around. J turns around. J goes from being positive to being negative. So J is not conserved, but the total amount of charge is conserved. That there's 1 coulomb of charge here going to the right becomes 1 coulomb of charge going to the left. The charge flow, the current, is itself not conserved. So every conserved quantity typically has a flow associated with it.
You drain a battery, charge is conserved. But the current, you drain a battery, the charge is conserved, but the current certainly is not the constant.
Right. Current itself is not conserved, charge is. But it's generally the case that conserved quantities have connected with them a flow of the conserved quantity. So total amount of water is conserved. The flow of water is not conserved, but there is a flow that's connected with the conserved quantity itself. That's, and we haven't discussed that connection, except to say that
say the field whose quanta are electrons, it has a phi 1 and phi 2.
Mm-hmm.
Do the phi 1 and phi 2 have any physical meaning that we can think of?
Not really. No more than saying out of it you can build these conserved quantities. Perhaps if we were a zillion times smaller, we would see these extra dimensions and see things moving around in them and say, oh, electric charge, oh, that's just the angular momentum of something spinning in one of the 10 dimensions of string theory or something. But from our perspective, what we get to see out of the whole thing is the electric charge, and that's about all. We don't get to see the internal motions that might be connected with it. We're too big.
You have an equation, the rate of change plus the divergence of a conserved quantity is always 0 or something?
Yeah, good. So that's what we're going to do next time. But if you want to jump ahead of the game a little bit, that's called the continuity equation. Continuity equation is that the time derivative of the density of charge plus the space derivatives, in just one dimension, this is derivatives, partial derivative, plus the space derivative of the charge flow, the current, is equal to 0. That's, of course, a statement. Well, I'll tell you what it's a statement of next time. And we'll want to check that. We'll want to check that that's a true statement, that it really behaves that way.
I thought of d rho dt, since rho is conserved, isn't that?
No, the integral of rho is conserved. The integral of rho is conserved. Right. So I'll tell you what this equation says. It says that if you have a region of space with some charge in it, the only way that the charge can change in that region is by a current flowing into or out of the region. So it says that you can't have a change in charge unless you have a current to carry that. You can't have a change of charge in a region unless there's a flow of charge out of that region or into that region. So it's the connection between the flow and the change of charge in a given region. And of course, what this says is that if there's a change of charge on the inside of this region, then there's a compensating change of charge on the outside of the region. So it's a kind of very local way of describing the conservation of charge. For example, what's not allowed is for charge, you might think that conservation of charge would allow the following: charge to disappear over here, and at the same instant that it disappears over here, to reappear over here. That would still satisfy the rules of conservation of charge. Total charge doesn't change. But that's not the way things work. The way they work is that charge gets from here to here by flowing through the region in between, so that you can detect the fact the charge is flowing from here to here by stationing yourself over here with a current detector and discovering the charges move through here. So conservation is more than just saying a quantity doesn't change. It says that when it does change, you can account for that change by a flow or a flux of the quantity through the boundaries of a region. And we're going to take that up, yeah.
Is there an experiment in physics that shows that that happens?
Oh, I'm sure there is. I'm sure there's a zillion, you know. Yeah, sure. I mean, can I think of an experiment offhand? No, but just think about what it means. It means that if you have a wire, and the charges move the charges just move along the wire, electrons move a little bit to the left. What happens? Well, let's take that case. Electrons in the wire all move to the right. What happens to the wire? What happens to the wire is some minus charge shows up over here, some plus charge shows up over here. Why? All the electrons have moved to the right. Each electron has moved to the right a little bit. Each one has moved to the right by the same amount. There's no buildup of charge in the interior, but there's an increase of charge, negative charge over here, because some one extra electron showed up here, one extra electron disappeared from here. So what you get is a net charge on the ends of the wire. That net charge on the ends of the wire happens all right, happens every time you put the wire in an electric field or something. But if you were to stand there and monitor what's going on, you would see a flow of charge across there. You wouldn't just see charge appear over here and disappear over here. You would see them all marching to the right. So yes, yes, there are, for example, every time a charge increases over here and decreases over here, a magnetic field due to the flow of charge in there is produced.
But what I'm thinking of is quantum tunneling, where it suddenly appears on the other side of the barrier. So that means that it must have been in the barrier at some time.
It was in the barrier, but there'll be a flow of charge to go with it. You'll see a sudden... if you have a detector in the barrier, it will detect that charge. Right. You can't make the charge go through the barrier. If there is a detector there, it will detect the charge. Yeah.
Would you say, kind of in general?
It'll also screw up the tunneling, but...
in general, at least in classical theory, that anytime you have some kind of a global law, that essentially there are local processes that it originates in?
Yeah. In fact, I would say that for most global laws, at least global conservation laws, but most global laws altogether, I can't think of any global laws except global conservation laws. But they tend almost always to be associated with local laws that are, as you say, not always. There are exceptions. Things called multiplicative quantum numbers, which are a little different. But, okay, so let's, yeah, if you want to study something, study the continuity equation, d rho dt plus dj dx.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.